What if everything you've ever experienced, every joy, every sorrow, every moment of your life has already happened before and will happen again in an endless cosmic loop? It sounds like something from science fiction, but some of the greatest minds in history, from ancient philosophers to modern physicists, have seriously considered the possibility that time is not a straight line but a circle, folding back on itself in ways that challenge our deepest assumptions about reality. We're about to explore the astonishing idea of temporal loops and universe cycles, concepts that stretch the imagination and invite us to rethink not just the nature of time, but the very meaning of existence. Throughout human history, the notion of cyclical time has surfaced again and again. Ancient civilizations from India to Central America built entire worldviews around the idea that history repeats, that the universe breathes in and out across unimaginable spans of time. Today, cutting-edge physics is breathing new life into these age-old intuitions, suggesting through theories like the Big Bounce, eternal inflation, and closed time-like curves that time may indeed fold, twist, and repeat on both the quantum and cosmic scales. What was once the domain of myth and metaphysics is now a vibrant area of scientific inquiry, blurring the lines between philosophy and physics in the most thrilling ways. In this video, we'll journey together through the most compelling theories of temporal loops, how they might work, what evidence might support them, and what they could mean for us as conscious beings living in what feels like a linear flow of moments. We'll see how black holes, quantum mechanics, and even the structure of spacetime itself might allow for the universe to reset, replay, and renew in an eternal dance. By the end, you may never look at time the same way again. You might just begin to see it not as a river carrying us inexorably forward, but as a vast, shimmering tapestry where every thread is connected, every moment eternal, and every ending also a beginning. So let's begin this journey into the folds of time. Long before telescopes or quantum equations, humans gazed at the stars and felt the turning of the seasons, arriving at a profound intuition that still captivates us today. That time itself might move in great, repeating circles. This ancient concept of cyclical time is a thread woven through countless cultures across the globe, each interpreting the cosmic rhythm in their own unique way. In the vast tapestry of Hindu philosophy, time is structured into immense epochs called yugas, each spanning thousands of years and marking a descent from a golden age of truth and enlightenment into a dark age of conflict and ignorance, only to eventually cycle back to the beginning again. This isn't just a measure of years, it's a spiritual map, suggesting that human consciousness and morality themselves rise and fall with these grand temporal waves. Similarly, the ancient Maya developed one of the most sophisticated and accurate calendar systems in history, centered around the concept of vast cycles of creation and destruction. Their long count calendar measured periods so immense that they saw our entire current existence as just one chapter in a much longer story, with each cycle ending in a transformation that paved the way for a new world age. This idea of a recurring cosmic pattern wasn't confined to any one continent. The ancient Greeks also grappled with these concepts. The philosopher Heraclitus, known for his doctrine that change is the only constant, famously suggested that the universe experiences an ever-living fire, kindling in measures and going out in measures, implying a periodic destruction and renewal of all things. Even more striking is the idea of eternal recurrence, later explored by thinkers like the Stoics and much later by Nietzsche, which proposes that the universe and all events within it have already occurred and will occur again identically, an infinite number of times. In the East, traditions like Buddhism and Jainism intimately link the cyclical nature of time with the spiritual journey of the soul through samsara, the endless cycle of rebirth. Here, time is not a neutral backdrop but an active participant in the law of karma, where actions in one cycle directly influence one's position and progress in the next. This transforms time from a simple measurement into a moral and evolutionary force. What's truly remarkable is how these diverse ancient systems, developed in complete isolation from one another, all converged on this same core idea: that time is a spiral, not a straight line. They observed the natural world, the daily path of the sun, the lunar phases, the annual seasons, and saw in these reliable cycles a hint of a much grander, metaphysical pattern. These weren't primitive superstitions. They were sophisticated attempts to find order and meaning in the cosmos, to understand humanity's place within it, and to grapple with the immense scales of existence. They offer a form of wisdom and even warning, suggesting that history, civilization, and perhaps even reality itself move through predictable phases of growth, maturity, decline, and renewal. This foundational perspective challenges our modern, linear view of history as a simple march of progress. It hints that our everyday experience of time flowing relentlessly forward might be just one small, local perception, a single thread in a much larger, infinitely repeating fabric. These ancient intuitions, born from observation and deep reflection, laid the essential groundwork for the astonishing scientific theories we continue to explore today. Yet for all its intuitive appeal, this ancient wisdom lacked a scientific framework, a language of mathematics to describe how such cycles could actually function within the fabric of the cosmos. That crucial framework arrived in the early 20th century, not from a philosopher contemplating the heavens, but from a patent clerk in Switzerland who would utterly dismantle our classical view of the universe. Albert Einstein's theories of relativity didn't just add a new chapter to physics, they rewrote the entire book, merging the separate concepts of space and time into a single, inseparable entity: spacetime. Imagine the universe not as a three-dimensional stage where time ticks away on a separate, universal clock, but as a four-dimensional fabric, a flexible sheet where every object with mass creates a dimple, a curvature. This is the heart of general relativity. The sun, for instance, isn't just floating in space. It's sitting in a deep well of its own making, and the planets are simply rolling along the curved contours of that well, which we perceive as the force of gravity. This idea that gravity is the geometry of spacetime, the bending of this four-dimensional fabric, leads to the most astonishing consequence. Gravity doesn't just bend the paths of objects, it bends time itself. This phenomenon, called time dilation, has been experimentally proven. Take two incredibly precise atomic clocks, synchronize them perfectly, then fly one around the world on a jet plane while the other stays on the ground. When you bring them back together, the clock that traveled will be ever so slightly behind the one that stayed. It experienced less gravitational pull and was moving at high speed, so time literally passed more slowly for it. Now amplify this effect to an extreme. Near a black hole where gravity is so intense that not even light can escape, this time warping becomes profound. An astronaut orbiting just outside the event horizon would age mere minutes, while decades or even centuries could pass for everyone back on Earth. Time is not a constant, universal river. It's a local stream, flowing at different rates depending on where you are and how fast you're moving. This malleability of time within the flexible fabric of spacetime opens the door to possibilities that sound like pure fantasy. Einstein's equations allow for solutions known as closed timelike curves. Think of a timelike curve as the path an object takes through spacetime. In our normal, flat spacetime, that path always moves forward into the future. But in a region of intensely warped spacetime like around a massively rotating black hole described by the Kerr metric, the equations show that this path could theoretically loop back on itself, connecting to its own past. An object following this path wouldn't be breaking any physical laws. It would simply be following the curvature of the universe, potentially arriving back at an earlier point in its own history. This isn't a suggestion that time travel is easy or practical, but it is a monumental revelation. The fundamental laws of physics, as best we understand them, do not explicitly forbid it. The architecture of reality, as described by Einstein, might inherently contain these folds, these loops where time could, in a sense, repeat or reconnect. Einstein's work, therefore, provided the essential mathematical groundwork that transformed cyclical time from a philosophical concept into a legitimate subject of physical inquiry. He gave scientists the tools to ask not just could time be a loop, but how could time be a loop? His equations are the rulebook, and within that rulebook, the plays for closed timelike curves and severe time dilation are all written out, waiting for the right cosmic conditions to run them. This shifted the debate from pure metaphysics into the realm of theoretical physics, setting the stage for every modern exploration into temporal loops, from the vast cycles of the cosmos to the strange behaviors of quantum particles. Relativity suggests that the universe's very structure might be woven with the threads of repetition, waiting for us to learn how to read the pattern. But if Einstein's relativity paints a picture of a flexible spacetime where loops are possible, it still largely assumes a universe with a single, definitive beginning, the Big Bang. What if that explosive start wasn't truly the beginning, but merely a turning point in a much grander, eternal rhythm? This is the captivating premise of the Big Bounce theory, a compelling alternative that reimagines our cosmic story not as a one-off event, but as an endless cycle of death and rebirth. Instead of a universe exploding from a single point of infinite density and heat, a singularity where our known laws of physics break down, the Big Bounce suggests our cosmos has been through this before. In this model, the universe expands from a hot, dense state as we observe, but eventually, the collective gravity of all matter and dark energy halts this expansion. The outward rush slows, stops, and then reverses, pulling everything back together in a grand cosmic contraction known as the Big Crunch. Imagine the entire universe, every galaxy, every star, every atom, collapsing inward upon itself. It's the ultimate gravitational collapse, not of a single star into a black hole, but of the entire cosmos. This is not necessarily an end, however. Proponents of the bounce suggest that just before the universe could crush itself into a meaningless singularity, quantum effects would take over. Think of it like compressing a spring. You can push it down, but at a certain point, it pushes back with tremendous force. In the same way, quantum repulsion, a phenomenon predicted by some interpretations of quantum gravity, could provide a POWERFUL Chinese letter, a rebound that stops the collapse and triggers a new Big Bang, birthing a fresh universe from the ashes of the old one. This new universe would then expand, evolve, and eventually contract again, continuing a cycle that could have been playing out for eternity, with no true beginning and no final end. This elegant idea solves one of the most frustrating problems in modern cosmology, the initial singularity of the Big Bang. The concept of a point of infinite density is a major roadblock for physicists because it represents a place where gravity becomes so strong that Einstein's equations simply fail. The Big Bounce elegantly avoids this problem. There is no true singularity, just a transition, a cosmic bounce where the laws of quantum gravity, which govern the ultra-small, step in to smooth out the infinite curvature and initiate a new phase. This makes the model particularly appealing within frameworks like loop quantum cosmology, which applies the principles of quantum mechanics to the universe as a whole. In this view, spacetime is not infinitely divisible but is woven from tiny, discrete loops, a fabric with a finite, smallest possible scale. This fundamental graininess prevents the universe from ever reaching a state of true infinite density, ensuring there's always a quantum force ready to initiate the bounce back into expansion. But is there any observable evidence for such a breathtaking idea? scientists are actively looking for clues. One promising place to search is the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. This ancient light is a snapshot of the infant universe, and some models of the Big Bounce predict that it might contain subtle imprints or anomalies, perhaps faint concentric circles or patterns. That could be echoes of a pre-bounce universe. While such evidence remains tentative and debated, the very possibility adds a thrilling empirical dimension to the theory. Furthermore, the observed acceleration of the universe's expansion, driven by dark energy, doesn't necessarily rule out a bounce. The nature of dark energy itself is still a profound mystery. Its properties could change over trillions of years, eventually weakening and allowing gravity to finally pull the universe back together. The Big Bounce theory doesn't ask us to discard what we know about cosmology, but rather to place it within a vastly larger and more dynamic context, a universe that breathes in and out across eons, each breath creating a new world with its own history, its own laws, and perhaps its own life. But if the Big Bounce reimagines our universe as a single, breathing entity, what if the true picture is even grander? What if our entire cosmos, with its hundreds of billions of galaxies, is just a single bubble in a frothing, infinite ocean of universes, each with its own unique physics and its own relationship with time? This is the mind-expanding realm of eternal inflation, a theory that takes the idea of cyclical time and scales it up to a truly cosmic level, suggesting that folds in time aren't just a feature of our universe, but a fundamental characteristic of reality itself. The story begins with the theory of cosmic inflation, which proposes that a fraction of a second after the Big Bang, our universe underwent an unimaginably rapid exponential expansion, smoothing it out and seeding the structures we see today. But what if that inflationary period never truly stopped? Eternal inflation suggests that this hyper-expansion is a perpetual state for the broader meta-universe, or multiverse. In this view, the energy field that drives inflation, often called the inflaton field, is like a landscape of hills and valleys. Most of this landscape is still up on the high-energy slopes, where inflation continues at a frantic pace, stretching spacetime faster than the speed of light. But occasionally, through random quantum fluctuations, a tiny patch of this field will tunnel downhill, settling into a lower energy valley. When this happens, the tremendous inflationary energy in that patch is suddenly released, and that release fuels a hot, dense Big Bang, birthing a new bubble universe within the ever-inflating background. Our entire observable universe is just one such bubble, and we are not alone. This process is happening endlessly, an infinite number of times across an infinite expanse. Each new bubble universe nucleates, expands, and cools, completely disconnected from all the others, forever separated by oceans of inflating space that are expanding too quickly to ever cross. Crucially, when each bubble forms, the specific way its local inflaton field settles determines the fundamental constants and laws of physics within it. In one bubble, the strength of gravity might be stronger, making stars burn out in millions of years instead of billions. In another, the nuclear forces might be too weak to ever form atoms. We find ourselves in a bubble with laws precisely tuned for complexity and life, not because it was designed, but because in an infinite multiverse, every possible set of laws will emerge somewhere, a concept known as the Anthropic principle. Now, consider time within this framework. If each bubble universe has its own distinct physics, then each one could have a completely different relationship with time. In our bubble, time seems to have a clear arrow moving from order to disorder. But in another universe, the arrow of time might be reversed, or time might be a two-dimensional surface, or it might be cyclical right from its very beginning. This is where the concept of temporal folding explodes in scope. A temporal loop that is impossible in our universe might be a commonplace occurrence in a neighboring bubble with different physical laws. Furthermore, the process of eternal inflation itself might be cyclical on a meta-scale. Some models propose that the inflattened field itself could undergo cycles, where old, dying bubble universes can somehow reignite the process of inflation in the broader multiverse, creating a self-sustaining cycle of creation that has no beginning and no end. Within this infinite tapestry, the life cycle of any single universe, from its hot Big Bang beginning to its eventual heat death or Big Crunch, is just a single blink in an eternal, multi-dimensional process. This means that folds in time are not merely a curious possibility within our local cosmic rules. They could be a ubiquitous feature across the multiverse. Some bubbles might be born from the collapse of previous ones, like in the Big Bounce model, but operating within the larger context of eternal inflation. Others might contain stable wormholes or closed timelike curves as natural parts of their spacetime geometry. The driving force behind it all, the inherent randomness of quantum fluctuations at the most fundamental level. These tiny, probabilistic events are the engines of creation, constantly giving birth to new realities, each with its own potential for temporal loops and cycles. Eternal inflation, therefore, offers the most expansive vision of cyclical time possible. It suggests that our entire history, from the formation of the first stars to the rise of human civilization, might be one infinitesimal thread in an infinitely repeating, infinitely varied multiversal pattern, where time itself is not a river but a vast, branching delta, flowing in every conceivable direction. While Einstein's relativity warps time and cosmic theories imagine great cycles of rebirth, quantum mechanics takes us to an even deeper, more radical level, a realm where time as we know it might not exist at all. This profound shift in perspective centers on one of the most ambitious and mind-bending equations in all of physics, the Wheeler-DeWitt equation. Conceived by physicists John Wheeler and Bryce DeWitt in the 1960s, this formula represents a heroic attempt to apply the bizarre rules of quantum mechanics not to particles or atoms, but to the entire universe at once. The result is a description of reality so foreign to our everyday experience that it completely upends our understanding of time itself. In the quantum world, particles can be in multiple places at once. They can tunnel through barriers, and their properties remain fuzzy until measured. The Wheeler-DeWitt equation treats the whole cosmos as one giant quantum object, and when you do that, something astonishing happens. The variable for time simply vanishes from the mathematics. It drops out completely. This suggests that at the most fundamental quantum level, the universe is timeless. There is no past, present, or future. Instead, the entire history of the cosmos from the Big Bang to the farthest reaches of the future exists all at once, frozen in a single, unchanging quantum state. Think of it not as a movie playing frame by frame, but as a single, intricate sculpture where every moment, from the formation of the first galaxy to you watching this video right now, is a fixed and permanent part of the structure. This is the concept of the block universe, or eternalism, but viewed through a quantum lens. What we perceive as the flow of time, the relentless march from one second to the next, is merely an emergent property, an illusion generated by our consciousness moving through this static landscape. We are like a reader tracing a path through a book. The story is already completely written, but we experience it sequentially, one word at a time. This timeless view has dramatic implications for the idea of temporal loops. If the entire universe is a single, frozen structure, then a loop in time isn't something that happens in time, it's simply a feature of the geometry of that structure, much like a spiral is a feature of a seashell. Closed time-like curves from general relativity would be pre-existing paths woven into this timeless block. A temporal loop would be an inherent part of the universe's architecture from the very beginning, not an anomaly or a strange exception. In this quantum picture, the past doesn't cause the future in a linear chain. Every event is interconnected and correlated within the whole. The Big Bang and the heat death of the universe are not separated by billions of years. They are simply two different locations in the cosmic sculpture, forever linked. This provides a potential resolution to the famous paradoxes of time travel. If the universe is static and self-consistent, then any event that appears to be a loop, like going back in time, was always part of the timeline. There was never a first version of history that got changed. There is only the one, complete, unchangeable history that contains the loop within it. The Wheeler-DeWitt equation, while immensely powerful theoretically, is not without its fierce critics and profound puzzles. Many physicists are deeply uncomfortable with the disappearance of time, an experience that feels so visceral and real to us. This is known as the problem of time in quantum gravity. How does our vivid illusion of a flowing present emerge from a fundamentally timeless foundation? Some theories suggest that time is not fundamental, but is a collective phenomenon that arises from the quantum entanglement of all the particles in the universe, a kind of cosmic synchronization that creates the appearance of a shared now. Others propose that our particular perspective within the universe creates the arrow of time, much like how looking at a landscape from one angle gives you a specific view, even though the entire landscape exists at once. Despite these challenges, the Wheeler-DeWitt equation remains a cornerstone in the quest for a theory of quantum gravity, forcing us to confront the possibility that our most basic experience of reality, the passage of time, is a beautiful and necessary illusion, and that the true nature of the cosmos is an eternal, interconnected whole where beginnings and endings are all part of the timeless pattern. But if the quantum realm suggests time is an illusion, we must return to the cosmos's most dramatic stages to find where this illusion might physically fold back on itself. Enter the universe's ultimate enforcers of relativity's wildest predictions, black holes. These cosmic monsters, born from the collapse of massive stars, are not just voids in space. They are profound engines of temporal distortion, where gravity becomes so overpowering that it twists the fabric of reality into knots. At the edge of a black hole at its event horizon, the gravitational pull is so intense that nothing, not even light, can escape. But the real magic for time folding happens just outside this point of no return, particularly around a specific type of black hole, a rotating Kerr black hole. Unlike a static black hole, a spinning one doesn't just pull spacetime inward, it drags it around in a swirling vortex, an effect known as frame dragging. Imagine stirring a cup of tea with a spoon. The liquid around the spoon is forced to rotate with it. A Kerr black hole does this to the very fabric of spacetime itself. This violent rotation creates a region just outside the event horizon called the ergosphere, where the dragging of spacetime is so extreme that it becomes impossible to stand still. Everything is forced to move with the black hole's spin. And within this chaotic region, the equations of general relativity reveal a breathtaking possibility: closed timelike curves. These are paths through spacetime that loop back on themselves. An object or a light beam following such a path could, in theory, travel on a trajectory that brings it back to the exact same point in both space and time from which it started. It wouldn't be traveling faster than light or breaking any laws. It would simply be riding the contours of spacetime as warped by the black hole's immense rotation. This isn't a guaranteed time machine. The energies and forces involved would be unimaginably destructive, and the practical challenges are beyond any conceivable technology. But the mathematics is clear. The architecture of a rotating black hole inherently contains these loops, these potential folds in time, written into the geometry of the universe by gravity itself. But what if you wanted a gentler, more navigable path through time? A cosmic shortcut rather than a terrifying plunge around a black hole? This is where another fantastical prediction of Einstein's equations comes into play. Wormholes, formerly known as Einstein-Rosen bridges. The concept is simpler to visualize than the math behind it. Picture the universe as a vast, two-dimensional sheet of paper. If you want to get from a point on the top to a point on the bottom, the long way is to travel across the entire length of the page. But if you could fold the paper so those 2 points touch, and then poke a hole through the contact point, you've created a shortcut, a tunnel connecting 2 distant locations instantaneously. A wormhole is that tunnel through the higher dimensions of spacetime. It would have 2 mouths connected by a throat, potentially linking not just different places, but different times as well. A stable, traversable wormhole wouldn't just be a space bridge. It could become a time machine. According to Relativity, if you were to take one mouth of the wormhole and accelerate it to a significant fraction of the speed of light, or place it in a strong gravitational field, time would pass more slowly for that mouth compared to the stationary one. After a while, you would have created a permanent time difference between the 2 ends. Walking into the stationary mouth might let you exit the moving mouth in the past. By creating a loop between the 2 connected points in spacetime, you could effectively create a closed timelike curve on demand, a man-made temporal fold. The catch, and it's a monumental one, is that according to our current understanding, such a wormhole would be incredibly unstable. The moment it formed, it would likely collapse into a singularity faster than even a photon could traverse it. Keeping it open would theoretically require a form of matter with negative energy density, so-called exotic matter, which repels rather than attracts gravitationally. While quantum mechanics allows for tiny amounts of negative energy in specific circumstances, whether it could be produced in the vast quantities needed to prop open a macroscopic wormhole is a question that pushes the very boundaries of known physics. So, while both black holes and wormholes remain speculative as practical mechanisms for time travel, their true value lies in what they teach us about the flexibility of the cosmos. They are not just science fiction tropes. They are serious mathematical consequences of our best theory of gravity. They illustrate that the universe's rulebook is far more permissive and imaginative than our everyday experience would suggest. These extreme cosmic structures act as natural laboratories, showing us the conditions under which space-time can be twisted, folded, and connected in ways that defy linear intuition. They provide concrete, if theoretical, models for how temporal folding could physically manifest, transforming the philosophical concept of cyclical time from an abstract wonder into a tangible possibility etched into the geometry of reality, waiting in the deepest reaches of space around its most mysterious and powerful objects. This leads us to one of the most profound and elegant explanations for why our universe seems so perfectly tailored for our existence, a concept known as the Anthropic principle. At its heart, it's a simple but incredibly powerful observation. The universe we observe must be compatible with the existence of observers, because if it weren't, we wouldn't be here to observe it. Think of it like this. A fish might wonder why the water it lives in is so perfectly suited for its gills, with just the right salinity and temperature. It's not that the water was magically designed for that one specific fish. It's that the fish evolved within that water, and any fish born into an environment that wasn't a perfect fit simply wouldn't survive to ponder the question. We are the cosmic equivalent of that fish. The fundamental constants of our universe seem almost miraculously fine-tuned for life. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, stars and galaxies never would have formed. If the nuclear strong force were a fraction different, the elements essential for life, like carbon and oxygen, wouldn't be forged in the hearts of stars. The list of these cosmic coincidences is long and staggering, making the odds of a life-permitting universe seem astronomically small. This is where the idea of cyclical time transforms from a mere physical mechanism into a potential answer to this deep existential puzzle. In a model where the universe undergoes endless cycles of birth, death, and rebirth, whether through a big bounce, eternal inflation, or another process, each new iteration can potentially have slightly different physical laws and constants. It's like rolling a colossal set of cosmic dice with every new cycle. For countless eons, the dice may have come up with numbers that produced universes that were stillborn, collapsing instantly, or expanding too rapidly for any structure to form, or lacking the fundamental forces to create atoms. These universes flash into and out of existence with no one to witness them. But eventually, through sheer probability across a near-infinite number of rolls, the dice will land on the perfect combination that allows for galaxies, stars, planets, and ultimately, conscious life. We find ourselves in this particular universe not because it's special or unique in a vast multiverse of failures, but because it's one of the rare winners, a universe that got the settings just right, allowing us to be here to marvel at it. The cycles aren't random, they are a vast, cosmic filtering process. Each reboot is another chance, another opportunity for the parameters to fall into the narrow window that permits complexity. Over enough cycles, a universe that can support observers becomes not just a possibility, but an inevitability. This perspective imbues the concept of temporal folding with a potential sense of direction or even purpose. Rather than a mindless, mechanical repetition, the endless cycles could be seen as a grand evolutionary process on a cosmological scale, slowly and inexorably moving towards greater complexity and consciousness. The folds in time aren't just loops. They are the turning pages of a story where the plot is the emergence of life and awareness from the cold, impersonal laws of physics. It suggests that the conditions for life aren't a bizarre fluke, but a natural outcome of a universe that has had countless opportunities to get it right. This doesn't require a designer or a guiding hand in the traditional sense. The mechanism is simply the relentless, probabilistic engine of cyclical time itself. The Anthropic principle, when married to these cosmological models, provides a stunningly elegant solution to the problem of fine-tuning. It tells us that we shouldn't be surprised by the apparent perfection of our universe. We are the living proof that after perhaps an eternity of trial and error, the cosmos finally stumbled upon a recipe that works, and we are here to savor the result, living in a golden age of a cycle that finally produced a world rich enough to ask questions about its own origin. While the Big Bounce and eternal inflation offer grand visions of cosmic cycles, they largely operate within the familiar four dimensions of spacetime. But what if the true engine of the universe's reset lies hidden in dimensions beyond our perception? This is the extraordinary proposition of the Ekpyrotic universe model, a theory that draws from the deepest wells of string theory to paint a picture of cosmic renewal that is both violent and elegant. The name itself comes from the ancient Greek word for conflagration, or out of fire, and it lives up to that dramatic origin. The model suggests our entire universe is a three-dimensional membrane, a brane for short, floating within a higher dimensional expanse. Think of our reality not as an isolated bubble, but as a single vast sheet of paper drifting in a multi-dimensional wind. Now, imagine another such sheet, another three-dimensional universe, floating on a parallel course in this hidden hyperspace. According to the Ekpyrotic scenario, the Big Bang was not a moment of creation from a singularity, but the aftermath of a cataclysmic collision between our brane and another one. This isn't a gentle bump. It's a head-on impact of unimaginable scale and energy. When these two immense, flat membranes smash into each other in the higher dimensional bulk, the kinetic energy of their collision is converted into an explosive fireball of radiation and matter, instantly heating a vast region of our brane to incredible temperatures. This release of energy, distributed with remarkable uniformity across the surface of our brane, looks for all intents and purposes exactly like the hot, dense state we identify as the beginning of our universe in the standard Big Bang model. In this view, the Big Bang was not the start of time, but a dramatic phase transition, a cosmic reset button pressed by a collision in a higher dimension. This framework provides a beautifully elegant solution to one of the major puzzles of the Standard Model, the initial singularity. The Ekpyrotic model completely avoids a point of infinite density and temperature. There is no mysterious genesis from nothing. Instead, there is a transfer of energy from the kinetic motion of the brains into the creation of a new hot universe on their surfaces. The brains themselves could have existed for eternity in the higher dimensional space, periodically drawn together by a weak attractive force, colliding and then bouncing apart, only to be drawn together once more in an endless, rhythmic dance. Each collision marks the beginning of a new cycle, a new expansion and cooling phase that gives rise to galaxies, stars, and life, all unfolding on the surface of the brain. Time, from our perspective within the brain, appears to begin with each bang, but from the higher dimensional view, it's a continuous process of oscillation, with each fold in the timeline occurring at the moment of impact. One of the most compelling aspects of this theory is its ability to explain the stunning uniformity of our universe, a problem that the inflationary theory was specifically designed to solve. When we look at the cosmic microwave background radiation, the oldest light in the universe, we see that it is almost perfectly smooth, with temperature variations of only 1 part in 100,000. How did regions of the universe that were too far apart to ever have been in contact with each other manage to achieve such a consistent temperature? Inflation solves this by proposing a period of ultra-rapid expansion that stretched a tiny, homogeneous patch into our entire observable cosmos. The Ekpyrotic model offers a different, equally fascinating solution. Because the colliding brains are inherently flat and can be nearly infinite in extent, the energy of their collision is deposited simultaneously and uniformly across a huge area. The resulting hot universe is born already smooth and homogeneous, without needing a separate inflationary epoch. Furthermore, the model naturally predicts specific patterns in the distribution of matter and the gravitational wave background that differ from those predicted by inflation, providing a potential way for future astronomical observations to test which theory might be correct. The implications for the nature of time are profound. In the Ekpyrotic universe, temporal folds are not just loops within a single spacetime continuum. They are events orchestrated from outside our dimensional prison. The cycle is driven by the dynamics of the higher dimensional bulk, a realm we cannot perceive directly. Each collision resets the clock of our universe, wiping the slate clean of all previous structure and information, and beginning a new cosmic story. It's a vision of cyclical time that is both grand and humbling, suggesting that the entirety of our reality is just a surface phenomenon, a temporary pattern arising from a much deeper, more complex dance happening in the hidden dimensions of string theory. This model doesn't just challenge our understanding of the Big Bang. It invites us to consider that the very fabric of our existence might be a mere shadow of a far richer, multi-dimensional reality, where time itself is reset by the slow, inevitable embrace of parallel worlds. Yet for all the grandeur of colliding brains and cosmic bounces, one of the most astonishing validations of cyclical behavior comes from a discovery not in the vastness of space, but in the controlled confines of a quantum laboratory, a discovery that fundamentally alters our understanding of matter itself. In 2016, researchers created the world's first time crystals, a new phase of matter that sounds like it belongs in a superhero comic, but is very, very real. To grasp what makes this so revolutionary, we first need to understand what a normal crystal is. Think of a diamond. Its beauty and strength come from its structure. Its atoms are arranged in a perfectly repeating, rigid pattern in space. This is spatial order. A time crystal flips this concept on its head. It's a structure that exhibits order and repetition not in space, but in time. Its internal components oscillate, or tick, in a stable, periodic cycle, even in its ground state, the lowest energy state possible. This last part is the true mind bender, and the reason time crystals sent shockwaves through the physics community. According to the traditional laws of thermodynamics, if you have a system in its ground state, it should be still. It has no extra energy to spend. It should be like a perfectly still pond, frozen in equilibrium. A pendulum at its lowest energy point doesn't swing. But a time crystal defies this. It's like a pendulum that, even at absolute rest, continues to swing back and forth forever without any friction or any energy input whatsoever. It's not a perpetual motion machine because it's not doing any work or producing energy. It's simply maintaining a persistent, unchanging rhythm, a beat that echoes through time itself. THIS, Chinese letter symmetry, but not a spatial symmetry like in a diamond lattice. It breaks time translation symmetry. In simple terms, the laws of physics are the same at every moment in time, so a system should look the same if you observe it at two different moments. But a time crystal doesn't. It changes over time in a regular, predictable pattern, all by itself, marking the passage of time with its own intrinsic clock. The creation of these crystals, first in diamond systems with nitrogen vacancies and later in chains of ytterbium atoms, required immense ingenuity. Scientists don't just find time crystals lying around. They have to drive them out of equilibrium to create this stable temporal order. They often use a periodic laser pulse to kick the system initially, but the magic is in the response. The time crystal doesn't oscillate at the same frequency as the laser. It responds at a fraction of that frequency, a clear sign that it has entered a new, stable phase of matter with its own independent rhythm. It's a system that locks into a cycle and stubbornly maintains it, resisting disruption and decay. This robustness is what makes it a true phase of matter, as distinct from a liquid or a solid. It's a state of being defined not by how its atoms are arranged, but by how they move through time in a coordinated, unending dance. So what does a microscopic quantum curiosity have to do with the grand cosmological cycles of the universe? The connection is profound and deeply suggestive. Time crystals provide the first ever physical blueprint for how a system can exhibit built-in, self-sustaining cyclical behavior. They are a literal, laboratory-scale example of a temporal loop. They demonstrate that under the right quantum conditions, repetition and periodicity can be fundamental, emergent properties of a system, not something that requires constant external energy to maintain. This opens a tantalizing door to a new way of thinking about the cosmos. Could the largest cycles we've been exploring, the Big Bounce, the Ekpyrotic collisions, somehow be reflections of this same principle operating on a universal scale? Is the universe itself, in some way, in a phase of matter that includes temporal order as one of its defining features? The existence of time crystals hints that cycles might not be an accident or a rare occurrence, but an inherent potential woven into the very fabric of physical law. Just as matter can crystallize in space, perhaps spacetime itself can crystallize in time. This doesn't mean the universe is a giant time crystal, but it shows that the quantum mechanical principles that allow for such bizarre states are universal. They govern the very small and, by extension, could influence the very large. Research into these strange new phases of matter is still in its infancy, but it already serves as a powerful bridge. It connects the esoteric world of quantum entanglement and symmetry, breaking directly to the philosophical and cosmological ideas of eternal return and cyclical time, providing a tangible, experimental foundation for the possibility that repetition is not just a feature of our universe, but one of its most basic building blocks. Now, if the universe truly contains these folds in time, these loops where the future can touch the past, we immediately slam into one of the most famous and terrifying thought experiments in all of science fiction, the grandfather paradox. Imagine you build a time machine, travel back to a time before your grandfather had children, and accidentally cause his death. If he dies before your parent is conceived, then you could never have been born to go back in time and kill him in the first place. It's a logical contradiction that seems to unravel causality itself, creating a paradox that should, by all rights, make temporal loops an impossible fantasy. It's this very problem that has led many to dismiss time travel as nothing more than a fun narrative device. But what if the laws of physics themselves have a built-in mechanism to prevent such nonsense from ever happening? This is precisely the bold and elegant solution proposed by Russian physicist Igor Novikov in the 1980s. He formulated the self-consistency principle, a deceptively simple rule that essentially says the universe is a closed, self-correcting system when it comes to causality. The principle asserts that any actions taken by a time traveler were always a part of history. There is no first run of events that gets altered. Your trip to the past is not an intrusion into a pristine timeline. It is an integral, immutable part of that timeline, and it always has been. Think of the universe not as a straight line that can be cut and retaped, but as a single, unchangeable story that has already been written in its entirety. In this story, if a time traveler appears in the past, their appearance and all their actions were always there, woven into the fabric of events. So, if you travel back with the intention of killing your grandfather, the principle dictates that you will inevitably fail. The gun will jam, you'll miss the shot, or you'll suddenly have a change of heart at the critical moment. Perhaps you'll trip on a loose floorboard and knock yourself out. The universe will conspire, through an infinite number of tiny, probabilistic events, to ensure that your actions do not create a contradiction. Your journey to the past doesn't change history, it fulfills it. Your presence there was always the reason your grandfather survived in the first place. Maybe you accidentally scared away a real assassin that day. The loop is closed, consistent, and paradox-free. Novikov didn't just pull this idea from thin air. He and his colleagues derived it from the mathematics of general relativity, particularly in the context of wormholes and closed timelike curves. The equations that allow for these temporal loops also seem to demand that they be self-consistent. Physics itself appears to abhor a paradox and has rules to prevent it. This has profound implications for the nature of reality and free will. The Novikov principle paints a picture of a deeply deterministic universe, a cosmic clockwork where every event, including our seemingly free choices, is fixed and unchangeable. If time travel to the past is possible, then your decision to use the machine was predetermined, and every action you take there was preordained to ensure the stability of the timeline. This doesn't necessarily mean you lack free will in a personal, experiential sense. You still feel like you are making choices, but it does mean that the entire history of the universe, from the Big Bang to the very end, is a single, frozen block where everything is interconnected and inevitable. This reinforces the idea that temporal folds are not glitches in the matrix or chaotic ruptures in reality. Instead, they are orderly, lawful, and elegant features of the cosmos. They are woven into the universe's lawful fabric, operating under strict rules that preserve cause and effect, even when those causes seem to come from their own future effects. The Novikov self-consistency principle doesn't just solve a science fiction puzzle. It offers a rigorous framework for how time travel could physically work without breaking the universe, turning a dream of chaos into a theorem of order. But if the Novikov principle suggests our timeline is a fixed and self-consistent story, then what is the true nature of the book in which that story is written? This brings us to one of the most profound and intellectually stunning models of reality, the block universe theory, also known as eternalism. This perspective doesn't just allow for time travel, it fundamentally redefines what time is, stripping it of all the qualities we intuitively assign to it. We experience life as a relentless flow, a river carrying us from the fixed past through the fleeting present and into the uncertain future. Eternalism argues that this sensation, while powerful, is a complete illusion. In this view, the universe is not unfolding, it simply is. Picture reality not as a movie playing on a screen, but as the entire DVD itself, a single, unchanging four-dimensional object where past, present, and future are all equally real and permanently encoded. Time in this model is not a flow but a dimension, just like length, width, and height. Your birth, you watching this video right now, and every moment of your future all exist simultaneously within this vast, static block of spacetime. There is no privileged now. The moment Julius Caesar was assassinated is just as real as the moment you first learned about it in a history book. They are simply located at different coordinates in the time dimension. This has a radical implication for the concept of temporal loops. In a flowing river of time, a loop is a bizarre and paradoxical anomaly, a whirlpool that seems to defy the current. But in a block universe, a temporal loop is not an event. It's simply a feature of the landscape. It is a geometric path through the four-dimensional structure where the world line of an object, the unique trail it carves through spacetime curves back on itself. A closed timelike curve around a rotating black hole, for example, would be a literal, physical spiral etched into the fabric of the block. From the perspective of eternalism, there's nothing paradoxical about this. The object traveling that loop was always on that path. Its journey into the past was always a part of the immutable whole. This view completely sidesteps the anxiety over changing history because, in a block universe, there is no history to change, only a fixed history to explore. Your future journey back in time is already a part of the past you intend to visit. The universe is a single, self-consistent tapestry, and temporal loops are merely the threads that cross back over themselves in an intricate, predetermined pattern. This challenges our deepest sense of self and free will. We feel we are agents of change, making decisions that shape an open future. Eternalism suggests that those decisions, and all their consequences, are already fixed in the grand structure of reality. This can feel deeply unsettling, as if we are merely passengers reading our lines from a cosmic script. However, many philosophers and physicists argue that this doesn't negate the experience of free will. Our consciousness might simply be a process that moves along our world line, experiencing each event in sequence, making choices based on the information available at that point in the block. The choice feels real to us because we are living through the process of making it. The entire timeline is fixed, but our journey through it is what gives meaning to our lives. The block universe theory doesn't make life pointless. It makes every moment eternally significant. Your happiest memories are not lost to the past. They are forever preserved at their specific coordinates in spacetime. Your hopes for the future are not uncertain. They are already out there, waiting for your consciousness to arrive. This perspective transforms the cosmos from a story being written into a magnificent, eternal sculpture. And our lives are the beautiful, intricate paths we take through its immutable form. This astonishing idea, known as the holographic principle, pushes our understanding of reality to its absolute limit, suggesting that the three-dimensional universe we experience might be nothing more than a projection, a cosmic illusion encoded on a distant, two-dimensional surface. It's a concept that sounds like it belongs in the realm of science fiction, but it emerges directly from the thorny physics of black holes and is one of the most revolutionary ideas in modern theoretical physics. To grasp it, consider an ordinary hologram like the kind you might see on a credit card. A flat, two-dimensional surface is etched with a specific pattern, and when light shines on it, it projects a seemingly three-dimensional image. The holographic principle proposes that our entire universe might work in a similar way. All the information that describes everything within a volume of space, every star, every planet, every person, and every event that happens within it could be entirely encoded on the two-dimensional boundary that surrounds that volume, like information painted on a giant spherical shell. This radical notion first gained traction from a fascinating paradox concerning black holes. When an object falls into a black hole, it seems to vanish completely, taking all its information with it. But this creates a terrible conflict with a fundamental rule of quantum mechanics. Information cannot be destroyed. It can be scrambled, but it must be preserved. The brilliant physicist Jacob Bekenstein discovered that the maximum amount of information or entropy that a region of space can contain is not proportional to its volume, as you might expect, but to the area of its boundary surface. This is bizarre. It's like saying the amount of information that can fit in your laptop isn't determined by the size of its hard drive, but by the surface area of its outer case. Stephen Hawking later showed that black holes actually radiate energy and slowly evaporate, intensifying the information paradox. Where does the information about what fell in go when the black hole disappears? The holographic principle offers a stunning solution. The information isn't lost inside the black hole. It's perfectly preserved, encoded on the black hole's event horizon, its two-dimensional point of no return. The three-dimensional interior, with all its terrifying mystery, is just a projection of that data. Now, apply this mind-bending logic to the entire cosmos. Some physicists, like Leonard Susskind, have proposed that we might all be living inside a hologram. The entire observable universe, with its vast three-dimensional expanse, could be a projection from information stored on a gigantic, spherical surface at the very edge of our vision, at the cosmological horizon. This flips our entire conception of reality on its head. In this view, space and time are not fundamental. They are emergent properties, like the image on a movie screen that arises from the pixels of light projected onto it. They emerge from the complex interactions of quantum bits of information living on that distant boundary. This suggests that the flow of time we experience so vividly might not be a fundamental feature of the universe, but a derived phenomenon, an artifact of how this cosmic information is processed and displayed. So what does this mean for the loops and folds in time we've been exploring? If time itself is emergent from information on a boundary, then a temporal loop might not be a physical twist in the fabric of spacetime, but rather a cycle in the way information is being processed and displayed. Think of it like a cosmic hard drive that contains the entire history of the universe. On that drive, the past, present, and future all exist simultaneously as stored data. A closed timelike curve could be represented as a self-referential loop in that data, a pointer that refers back to an earlier part of the file. From our perspective inside the projection, it would feel like we are living through a repeating sequence of events, but from the outside perspective on the boundary, it's simply a specific, self-consistent pattern of information. The universe's history isn't happening and then repeating. It is a single, static, informational structure that contains loops within it. This provides a powerful new lens through which to view the universe's potential cyclical nature. The great cycles of the Big Bounce or the Ekpyrotic model could be understood as the cosmic hard drive undergoing a reboot, where the information on the boundary is reconfigured and a new three-dimensional projection, a new universe cycle is generated. The holographic principle connects the physics of gravity and spacetime directly to the physics of information, suggesting that the conservation of information is the most fundamental law of all. In this breathtaking framework, the folds of time are not wrinkles in a fabric, but intricate, self-referential patterns in the ultimate code of reality. Patterns that cycle and repeat as the cosmos executes its grand, incomprehensible program. This profound human fascination with time's circular nature isn't confined to ancient texts or philosophical musings. It is a vibrant, living tradition that continues to captivate us through the stories we tell. Modern storytelling has become a powerful vessel for exploring these complex ideas, translating abstract theories of temporal loops into deeply personal and emotionally resonant narratives. The film Groundhog Day presents a brilliant and accessible metaphor, trapping its protagonist in a single, repeating day where escape is only possible through genuine self-improvement and moral growth. The loop is not a punishment but a crucible, forcing him to break free from his own patterns of selfishness and cynicism. This narrative brilliantly mirrors the spiritual concept of samsara, where the cycle of rebirth continues until one achieves enlightenment. It resonates because it taps into a universal human experience, the feeling of being stuck in a rut, and the transformative power of breaking free from our own mental and emotional repetitions. The time loop becomes a powerful allegory for redemption, suggesting that our personal history is not a fixed sentence but a cycle we can learn from and ultimately transcend. On a grander, cosmic scale, a film like Interstellar uses the fabric of spacetime itself as a narrative device. Here, the protagonist doesn't just travel back in time. He manipulates gravity to communicate across dimensions, creating a causal loop where he is both the receiver and the sender of the crucial information that saves humanity. This isn't just a clever plot twist. It's a visceral exploration of concepts like closed timelike curves and the block universe, where love and connection are portrayed as forces that can literally bend time. The film masterfully blends cutting-edge scientific concepts, informed by physicist Kip Thorne, with a profound emotional core, making the fifth-dimensional physics of a tesseract feel intimately connected to a father's love for his daughter. These stories work because they satisfy a deep-seated human intuition. That time is not a simple line, but a complex, interconnected whole where the past, present, and future are in a continuous, meaningful dialogue. This cultural exploration reveals something essential about the human condition. Our obsession with cyclical time in myth and story is more than just entertainment. It is a fundamental part of how we make sense of our own existence and possibilities. These narratives provide a framework for understanding the world that is often more intuitive than a dry scientific equation. They allow us to grapple with the anxiety of chaos by imposing a pattern of order and return. They offer hope in the form of second chances, redemption, and the idea that no mistake is truly final in a universe that might allow for revision. The phoenix doesn't just die and rise again. It is reborn from its own ashes, transformed and renewed, symbolizing a resilience that is baked into the very order of reality. Similarly, Nietzsche's thought experiment of the eternal recurrence, asking us to live our lives over and over again, identical in every detail, isn't meant as a cosmological fact but as an ethical challenge. It forces the question, if this moment were to repeat forever, would you live it with regret or with profound affirmation? This philosophical device uses the idea of a temporal loop to push us toward a more authentic and passionate engagement with our own lives. By weaving these themes into the fabric of our culture, from ancient epics to blockbuster films, we are participating in a timeless conversation. We are using the tools of narrative to explore the same mysteries that physicists probe with mathematics and telescopes. These stories give shape to our deepest fears and highest hopes about the nature of reality. They allow us to experience, safely and emotionally, the dizzying implications of a folded timeline, making the abstract tangibly human. This demonstrates that the scientific pursuit of understanding temporal loops and the artistic exploration of them are not separate paths, but complementary journeys toward the same truth. They both stem from a shared desire to find meaning, pattern, and perhaps even a sense of purpose within the vast and often incomprehensible flow of time. But if the holographic principle suggests our reality is a projection, and storytelling explores its emotional weight, we must confront the most fundamental physical property that seems to define our experience of time: entropy. Often described as the measure of disorder in a system, Entropy is the reason we remember the past but not the future. The reason an egg can be scrambled but never unscrambled. And the reason the universe appears to have a one-way street running straight from a state of exquisite order to one of ultimate chaos. This relentless march toward disorder is what physicists call the arrow of time, and it feels as absolute and undeniable as gravity itself. It's the reason the concept of time folding back on itself seems so paradoxical. How can time loop if it's always flowing downhill? Yet, this very conflict is where the most fascinating possibilities for cyclical universes emerge, proposing that entropy, the great engine of time's arrow, might not be a permanent sentence but a phase that can be reset. To truly grasp this, we need to understand entropy not just as messiness, but as a statistical inevitability. Imagine a new deck of cards, perfectly ordered by suit and number. This is a low entropy state. Now, shuffle that deck once. It's slightly less ordered. Shuffle it 1,000 times, and the cards will be in a state of maximum disorder. A high entropy state where any specific arrangement is just as random as any other. The universe started in an incredibly low entropy state, a hot, dense, and extraordinarily smooth soup after the Big Bang. Ever since, it has been shuffling itself, with stars forming and dying, galaxies colliding, and energy dissipating. The ultimate fate in this model is the heat death of the universe, a state of maximum entropy where everything is so evenly spread out and cold that no work can be done. No stars can shine, and no life can exist. Time, in this view, becomes meaningless because there are no processes left to mark its passage. This presents the single greatest challenge to any model of a cyclical universe. If entropy always increases, how can the universe possibly reset itself for a new cycle? Wouldn't each subsequent cycle start with even more disorder than the last, making the bounce weaker and the resulting universe more chaotic until the whole process grinds to a halt? This seems like a logical deal-breaker, but theorists behind models like the Big Bounce have a profoundly clever retort. They propose that entropy doesn't have to be preserved across the bounce point. Think of the cosmic cycle not as a simple oscillation, but as a transformation. During the Big Crunch phase, as the universe collapses, gravity, the great organizer, takes over from the other forces. While everyday processes increase disorder, the immense gravitational pressure of a collapse could actually work to smooth things out, erasing the complex structures like galaxies and stars and wiping the cosmic slate clean. The universe is compressed back into a hot, dense, and homogeneous state, effectively resetting entropy to a low value ready for the next expansion. In this breathtaking scenario, the arrow of time is not an absolute law of the entire cosmos, but a local phenomenon specific to each cycle. During the expansion phase of our universe, entropy increases and time has a clear direction. But at the moment of the bounce, during the transition from crunch to bang, the arrow of time could flip or become undefined. From our perspective within a cycle, time's flow is irreversible, but from a God's eye view outside the cycles, time is just a pendulum swinging back and forth, with each swing representing a new universe with its own arrow emerging from the reset. This doesn't violate the fundamental laws of thermodynamics. It recontextualizes them. The total entropy of the entire multiverse or meta-universe might still be increasing, but our local pocket of reality gets a fresh start with each new cycle. This elegant idea reconciles the undeniable forward march we experience every day with the grand, poetic vision of an eternal return, suggesting that the flow of time itself is cyclical, breathing in and out between order and chaos. Yet for all their philosophical intrigue and narrative appeal, the true power of closed timelike curves lies not in storytelling but in the cold, precise language of mathematics, a realm where their beauty and their problems are laid bare with stunning clarity. These are not mere speculative ideas. They are rigorous solutions to the most profound equations ever written, emerging directly from the fabric of Einstein's general relativity. The mathematics reveals that under specific, extreme conditions, the shortest path between 2 points in spacetime might not be a straight line or even a gentle curve, but a loop that circles back to its own beginning. This isn't a bug in the equations, it's a breathtaking feature, a direct consequence of allowing mass and energy to warp the four-dimensional geometry of the universe. The formulas show that in the presence of an immensely rotating body, like a Kerr black hole, the dragging of spacetime can become so severe that light cones, the fundamental boundaries of possible movement for any object, tip over until they point backwards in time. In this warped region, your future could literally become your past, and the mathematics provides a perfectly self-consistent, if bewildering, map for the journey. This mathematical elegance, however, comes hand in hand with profound paradoxes that threaten the very logical foundations of physics. The most famous is the grandfather paradox, where a time traveler could prevent their own existence, creating a logical inconsistency that should be impossible. But the equations of general relativity themselves don't seem to care about this paradox. They simply allow for the CTC to exist as a geometric possibility. This forces physicists to confront a deep question: do the laws of physics somehow prevent such contradictions from occurring, or is our understanding of causality itself incomplete? Some researchers, like Igor Novikov, proposed a resolution through the self-consistency principle, which the mathematics can accommodate. In this view, the equations only permit CTCs that are entirely self-consistent. Any attempt to create a paradox would be thwarted by the laws of probability or quantum mechanics, ensuring that events within the loop are fixed and unchanging. You might travel back in time, but you could never change the past in a way that alters the future that sent you back. The loop is preordained, a stable mathematical knot in spacetime. To test these incredible ideas, physicists explore specific theoretical constructs where CTCs might emerge. The most promising venue is the ergosphere of a rapidly spinning Kerr black hole, where frame dragging is so extreme that these loops can theoretically form. Another exotic possibility involves cosmic strings hypothetical, infinitely long one-dimensional defects in spacetime left over from the early universe. If two such strings were to move past each other at high speed, their immense gravitational fields could warp spacetime enough to create CTCs in their wake. Researchers also delve into the implications of wormholes, or Einstein-Rosen bridges. The mathematics shows that if you could take one mouth of a traversable wormhole and accelerate it to near light speed or place it in an intense gravitational field, you would create a time difference between the two ends. Walking through the wormhole would then be a journey not just across space, but across time, effectively creating a man-made closed timelike curve. These aren't just fun thought experiments. They are serious calculations that push general relativity to its absolute limits, probing the boundaries between the possible and the impossible. Ultimately, the study of closed timelike curves is a testament to the incredible power of mathematical beauty as a guide in theoretical physics. Even when a concept seems to defy all intuition and practical experience, if the equations allow it and the geometry is elegant, it demands serious consideration. This pursuit has led to a much deeper understanding of the nature of causality, the relationship between quantum mechanics and gravity, and the fundamental structure of spacetime itself. While no evidence exists that CTCs are real or stable in our universe, and many physicists believe quantum effects would likely prevent them from forming, their mathematical reality forces us to expand our imagination. They stand as a brilliant, challenging reminder that the universe described by our best theories is far stranger and more wonderful than our everyday experience suggests. A place where time itself can, in principle, fold into loops of breathtaking geometry and profound mystery. This brings us to one of the most deeply personal and philosophically charged questions raised by all these theories. If the universe is caught in an endless cycle of repetition, where does that leave us? If every event, from the birth of a star to the choice you're making right now, has already happened an infinite number of times and will happen again, does that mean our lives are nothing more than a recording playing on a cosmic loop? This is the ancient tension between determinism and free will, and the concept of temporal loops pours rocket fuel on the debate. Hard determinism argues that if the universe is a closed, physical system, whether a single block or a repeating cycle, then every event is the inevitable result of prior causes, tracing all the way back to the initial conditions of the cosmos. In this view, the feeling of making a choice is an illusion. The outcome was predetermined billions of years ago. Your life is a story that has already been written, and you are merely reading the lines. Temporal loops seem to amplify this, suggesting we are actors performing the same script for eternity, trapped in a narrative with no possibility of deviation. Yet, this stark conclusion is not the only way to see it. Another school of thought, known as compatibilism, offers a more nuanced and perhaps more comforting perspective. Compatibilists argue that free will and determinism are not mutually exclusive. They redefine free will not as the magical ability to act outside the chain of cause and effect, but as the capacity to act according to your own desires, motivations, and character, without external coercion. In a cyclical universe, even if the entire sequence of events is fixed, your actions are still your actions. They spring from who you are. The fact that you might make the same choice in every cycle doesn't make it any less your choice. It simply reflects the consistent nature of your character. From this viewpoint, a temporal loop doesn't rob you of agency. It affirms that your identity is so fundamental that it plays out the same way every time, making you an integral and authentic part of the cosmic pattern. Perhaps the most fascinating possibility lies in the middle ground. What if the cycles are not perfect photocopies? Quantum mechanics introduces fundamental randomness and probability into the universe. This opens the door to the idea that each cosmic cycle, each iteration of a temporal loop, might not be an exact replica. There could be tiny, quantum-level variations that ripple up through each new cycle, creating differences each time around. In this model, the universe is not repeating identically but evolving through each cycle, learning and changing like a musician improvising on a theme. This means that even within a grand, cyclical framework, there could be room for genuine novelty and growth. Your choices in one cycle could influence the starting conditions of the next, not by changing the past of your own timeline, but by seeding a new variation in a future iteration. This transforms the concept of eternity from a prison into a classroom, where the goal is not to escape the loop, but to learn and evolve within it, making each cycle a step toward a greater understanding or a higher state of being. This shifts the question from a cold, physical problem into a profoundly human one. It's no longer just about the mechanics of space-time, but about the meaning we assign to our lives within that structure. If our actions are part of a cycle, does that make them less significant, or does it make them more so? The philosophy of eternal recurrence, most famously associated with Friedrich Nietzsche, treats this not as a scientific theory to be proven, but as an ethical thought experiment. He asked, "What if a demon whispered to you that you will live this exact life, with every joy and every pain, repeated infinitely? Would you despair at the thought, or would you embrace it with a triumphant yes?" This challenge is about radical self-acceptance and responsibility. It forces you to consider whether you are living a life you would be willing to relive forever. In doing so, it doesn't demand that you believe the cycles are real. It demands that you live as if they are, investing each moment with ultimate significance because it will echo through eternity. This philosophical stance injects purpose into the loop, suggesting that our sense of agency and meaning isn't derived from breaking free of cosmic patterns, but from fully embracing our role within them and striving to make that role one we can be proud of, cycle after cycle after cycle. But how do we move from these breathtaking theoretical possibilities to tangible, observable evidence? How do we test the seemingly untestable? The answer lies in the relentless ingenuity of modern science, where physicists are devising ingenious ways to search for the fingerprints of previous cosmic cycles, transforming metaphysical wonder into a rigorous experimental pursuit. One of the most promising hunting grounds is the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This ancient light is a fossilized snapshot of the universe when it was just 380,000 years old, and it is etched with tiny temperature fluctuations, the seeds that would eventually grow into the vast cosmic web of galaxies we see today. For proponents of cyclical models like the Big Bounce, this CMB map is a potential treasure trove. The violent events of a previous cosmic cycle, particularly a pre-Big Bang contraction phase, could have left faint but distinctive imprints on this radiation. Some theories suggest that the gravitational waves generated during the collapse of a prior universe might have created concentric circular patterns or specific statistical anomalies in the CMB's polarization. It's like searching for faint, ghostly ripples on the surface of a pond, evidence of a stone thrown in long before we arrived. Teams of researchers meticulously analyze data from space telescopes like Planck, searching for these telltale signs, a statistical whisper from a universe that existed before our own. While no definitive evidence has been found yet, the very fact that we know what to look for is a monumental step forward. Beyond the silent glow of ancient light, scientists are also listening for the echoes of creation through gravitational wave astronomy. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by directly detecting these ripples in spacetime from colliding black holes and neutron stars, opening an entirely new window onto the cosmos. For cyclical universe theories, this new sense holds incredible potential. The unimaginable energies involved in a big crunch or a brain collision would have generated a deafening roar of gravitational waves, a cosmic cacophony that would have reverberated through the fabric of reality. While the specific signal from our universe's birth would be buried in the background, hiss of more recent events, future, more sensitive detectors like the proposed space-based Laser Interferometer Space Antenna, or LISA, might be able to tease out this primordial gravitational wave background. Finding a specific signature in this background could be the smoking gun, direct evidence of the violent events that sparked our cosmic cycle. It would be like hearing the faint, deep echo of the drum that signaled the beginning of time as we know it. The search isn't confined to the vast scales of cosmology. It also takes place in the incredibly controlled, high-energy environments of particle accelerators like the Large Hadron Collider. While we cannot recreate the energies of the Big Bang itself, we can probe the extreme states of matter that might mimic conditions at the bounce point, or in the early moments of a new cycle. By smashing particles together at nearly the speed of light, physicists can create a quark-gluon plasma, a primordial soup of matter that hasn't existed since the universe's first microseconds. Studying the behavior of this plasma, how it flows and thermalizes, provides critical clues about the fundamental laws that govern matter under such extreme pressure and density, the very laws that would dictate how a universe collapses and rebounds. Furthermore, the hunt for new particles and forces, such as those predicted by supersymmetry or string theory, could reveal the underlying physics that makes a cyclical cosmos possible, giving us the mathematical rules for how spacetime can fold and reset without violating the conservation of energy or information. Perhaps the most revolutionary experimental front is emerging not from massive telescopes or colliders, but from the quantum realm itself. The recent creation of time crystals in laboratories around the world provides a tangible, albeit microscopic, model of a system with built-in temporal order. By studying how these strange phases of matter maintain their oscillation without energy input, physicists are gaining insights into how cyclical behavior can be an inherent, stable property of a system's ground state. This doesn't prove the universe is a time crystal, but it demonstrates that the quantum mechanical principles enabling such behavior are real and testable. Similarly, advanced quantum simulations are allowing researchers to model the conditions of closed timelike curves on quantum computers, exploring how information would behave in a self-consistent loop, and testing the limits of causality without the need for a black hole. These tabletop experiments are providing a new, practical way to explore the physics of time loops, offering a glimpse into the logical rules that might govern a cyclical cosmos. Each of these efforts, from the cosmic to the quantum, represents a different strand in a vast web of inquiry. They are the methods by which we are slowly, painstakingly learning to read the universe's deepest diary, searching for an entry that began. Before this, there was. Imagine for a moment that the most profound scientific and philosophical theories we've explored weren't just abstract concepts, but were proven to be true. How would that knowledge reshape your mind, your choices, and your very sense of self? This is the fascinating crossroads where cosmology meets psychology, where the architecture of the universe collides with the inner workings of human consciousness. Believing that time is cyclical, that our lives and our world might be part of an endless series of repetitions, isn't just an intellectual exercise. It's a psychological lens that can dramatically alter our perception of reality, responsibility, and meaning. The most famous thought experiment on this comes from the 19th century philosopher Friedrich Nietzsche and his concept of the eternal recurrence. He proposed a daunting challenge. What if a demon whispered to you that you will live this exact same life, with every identical joy and every identical pain, repeated an infinite number of times? Your immediate, visceral reaction to that idea is a powerful mirror into your psyche. For some, this thought is a prison sentence, a source of profound despair or existential dread. The idea that no mistake is ever truly left behind, that suffering is eternal, and that escape is impossible. This perspective can lead to a kind of nihilistic paralysis, a feeling that nothing ultimately matters because everything is predetermined and endlessly recurring. Yet for others, this very same idea becomes the ultimate catalyst for a life of intense purpose and authenticity. Nietzsche intended it not as a cosmological fact, but as the ultimate ethical test. If you knew you'd relive every moment forever, would you be filled with regret? Or would you embrace your life with a triumphant yes? This shifts the focus from fate to attitude. It demands a radical form of self-acceptance and responsibility. Every action, no matter how small, is imbued with eternal significance. You become the author of a story you are proud to read again and again. This isn't about changing the past, but about fully owning the present, making choices aligned with your deepest values because they will define your existence for eternity. This mindset can foster incredible personal growth, pushing individuals to break free from negative patterns, to cultivate gratitude, and to seek out experiences that make life worth repeating. It transforms the cycle from a trap into a classroom where the goal is to learn, to evolve, and to live so completely that the prospect of repetition is not a threat, but a celebration. This philosophical shift has powerful, practical implications for how we interact with the world and each other. Consider environmental stewardship. In a linear view of time, where the universe has a definitive end, there can be a dangerous temptation to prioritize short-term gains over long-term sustainability, a use-it-now mentality. But if time is cyclical, and future iterations of humanity will inherit the same planet, perhaps in a renewed form after a cosmic reset, then our responsibility deepens exponentially. Polluting a river or driving a species to extinction isn't just a problem for our grandchildren. It's a problem for infinite future versions of ourselves and our civilization. This belief could forge a powerful planetary ethic, a drive to protect and preserve not for some abstract future, but for the countless cycles of life yet to come. Our role transforms from temporary tenants to eternal custodians of a world that will be reborn again and again. On a more intimate scale, the psychology of cyclical time can reframe our approach to personal challenges and relationships. Viewing life as a series of learning loops can be incredibly liberating. A failed relationship or a career setback is not a permanent stain on a linear timeline. It becomes one iteration in a long process of growth. It's the cosmic equivalent of practice makes perfect. This perspective encourages resilience, patience, and self-compassion. It suggests that we have endless opportunities to get it right, to learn from our mistakes, and to approach each new day, or each new cycle, with the wisdom gained from the last. This can alleviate the immense pressure of modern life to achieve perfection in a single, fleeting lifetime. It allows for the beautiful, human process of trial and error, of slowly becoming better versions of ourselves across what might be an infinite journey. Ultimately, the psychological impact of believing in cyclical time reveals a profound truth about humanity. Our world, is not a passive reception of facts, but an active framework that shapes our emotions, our ethics, and our actions. Whether these theories are ever scientifically proven may be less important than the questions they force us to ask about how we want to live. They challenge us to find meaning not in spite of the universe's mysteries, but within them. They remind us that our search for understanding in the cosmos is inextricably linked to our search for understanding within ourselves, and that the folds of time might just be reflected in the endless, evolving patterns of the human heart. While physicists and philosophers debate the mathematics and metaphysics of time loops, popular culture has been busy bringing these mind-bending concepts to life, transforming abstract equations into gripping emotional journeys that resonate with millions. The small screen has become a particularly powerful canvas for exploring temporal folding, with shows like the long-running British series Doctor Who using time travel not just as a plot device, but as a fundamental aspect of its hero's identity. The Doctor isn't just a space adventurer, he's a Time Lord, a being with a deeply personal and often painful relationship with the flow of history. The show's famous TARDIS is more than a machine. It's a vehicle for exploring the ethical weight of causality, often presenting the Doctor with heart-wrenching dilemmas where saving one life could unravel all of reality. This personification of time's mysteries makes the science feel intimate, teaching audiences about fixed points in time and the potential paradoxes of interference through the emotional lens of a character we've grown to love over decades. But for a truly masterclass in the narrative potential of cyclical time, one must turn to the German Netflix series Dark, a show that treats the concept of temporal loops not as a gimmick, but as the very DNA of its storytelling. Dark is a sprawling, intergenerational saga where time travel is both a curse and a cosmic mechanism, connecting the fates of 4 families across multiple centuries in the small town of Winden. The series doesn't shy away from complexity. It embraces the full implications of a deterministic, closed-loop universe. Characters don't just travel to the past. They discover that their attempts to change events are the very reason those events happened in the first place. A character trying to prevent an apocalypse inadvertently causes it, and a man's quest to find a missing child ultimately ensures that child is lost. This is a direct and brilliantly executed narrative illustration of the Novikov self-consistency principle, where the universe conspires to prevent paradoxes, making every action part of a predestined, unchangeable whole. Dark uses its intricate plot to visualize concepts like causal loops and the block universe theory, showing us a reality where everything is interconnected, and the future can literally write the past. These creative explorations, while taking artistic license, perform an invaluable service. They act as a gateway drug for scientific curiosity. A viewer captivated by the bootstrap paradox in dark where an object or piece of information has no discernible origin, existing in a cycle of its own creation, might be inspired to look up the term online, leading them down a rabbit hole of articles about ontological paradoxes and the works of physicists like John Wheeler. The show's depiction of a triqueta-shaped knot of time, linking three distinct eras, is a stunning visual metaphor for the non-linear nature of causality in a folded spacetime. Similarly, the film Interstellar, with its scientifically informed depiction of a tesseract, a higher dimensional space where time becomes a physical dimension, gave audiences a visceral, if theoretical, feel for what a four-dimensional continuum might look like. This kind of storytelling doesn't just entertain, it educates by immersion, making the audience feel the consequences of twisted time in their guts through character and conflict, rather than just reading about it in a textbook. This cultural fascination reveals a deep, almost primal human need to make sense of time's mysteries through story. We use narrative as a safe playground to experiment with frightening ideas, to ask, what if, without real-world consequences? The time loop comedy Groundhog Day is a perfect example. On the surface, it's a hilarious story about a cynical man trapped reliving the same day. But at its core, it's a profound philosophical exploration of karma, self-improvement, and the search for meaning. The loop is not a punishment but a crucible, forcing the protagonist to break free from his own spiritual stagnation. This mirrors ancient Eastern concepts of samsara, the cycle of rebirth driven by karma, where enlightenment is achieved by escaping the wheel of repetition. By wrapping this ancient wisdom in a modern, relatable comedy, the film makes a profound philosophical argument accessible to everyone. It demonstrates that the appeal of temporal loops isn't just about the mechanics of time travel. It's about what these cycles say about us, our capacity for change, and the patterns we struggle to break in our own lives. Ultimately, the portrayal of time loops in popular culture serves as a vital bridge, connecting the rarefied air of theoretical physics with the lived experience of everyday wonder. These stories democratize complexity, allowing anyone with a Netflix subscription or a movie ticket to grapple with the same profound questions that occupy the world's greatest scientists and philosophers. They spark conversations around dinner tables and in online forums, inspiring a new generation of thinkers to look at the night sky not just with awe, but with a newfound curiosity about its deepest operational secrets. By transforming mathematical abstractions into human dramas of fate, free will, and redemption, popular culture doesn't dumb down the science. It amplifies its emotional and philosophical resonance, ensuring that the timeless mystery of time itself remains a vibrant and essential part of our collective imagination. But the moral quandaries don't stop with paradoxes. They extend into the very heart of human agency and justice. Imagine possessing a time machine and learning of an impending natural disaster or a terrible crime. Your ability to intervene creates an immense ethical burden. Would you have a moral obligation to prevent every tragedy throughout history? This sounds noble, but the consequences could be catastrophic. Preventing a single plague might alter population dynamics so drastically that it prevents the birth of a future leader whose decisions avert a global war. Your well-intentioned act of saving thousands in the past could inadvertently doom millions in the future, a terrifying illustration of the butterfly effect on a cosmic scale. This transforms the time traveler from a mere tourist into a godlike figure, burdened with impossible calculations, where every action carries unintended ripple effects across centuries. The weight of that responsibility is enough to paralyze any sense of moral duty, raising the disturbing question of whether it is ever ethical to act when the full consequences are inherently unknowable. This leads directly to the problem of consent and autonomy on a scale we can scarcely comprehend. If you travel to the past and interact with people, you are essentially manipulating their lives without their knowledge or consent. They are operating with limited information, unaware that the stranger offering them advice is actually a time traveler who knows the outcome of every decision they will make. This creates a fundamental power imbalance, reducing people in the past to pawns in a game whose rules only you understand. It's the ultimate violation of autonomy, treating entire eras as experimental playgrounds rather than realms where people have the right to live their lives free from external, futuristic manipulation. Even a seemingly benign act, like giving a struggling inventor a crucial idea that leads to a world-changing technology, robs that person of their genuine creative journey and the satisfaction of their own achievement. The ethical course might be one of total non-interference, a prime directive for time travelers, but the temptation to fix things would be overwhelming, constantly testing the resolve of anyone with such power. The ethical landscape becomes even stranger when we consider the implications within a truly cyclical universe, where the same events replay infinitely. If you were to discover that you are living inside such a loop, does that change your moral obligations? On one hand, if every action is predetermined and will happen identically again and again, then personal responsibility seems to vanish. Why bother trying to be good if your misdeeds are etched eternally into the fabric of reality with no possibility of change? This could lead to a dangerous moral nihilism. Conversely, this knowledge could inspire the ultimate form of ethical living. If you are destined to relive every moment forever, then you have the strongest possible incentive to make each iteration a good one, to treat others with kindness and to act with integrity, because you and everyone else are condemned to experience the consequences of your actions for eternity. Your ethical choices are magnified from fleeting moments into eternal truths. This isn't about changing the loop. It's about perfecting your role within it, striving to create a cycle worth repeating. These are not merely abstract puzzles for philosophers. They force us to reflect on the ethics of our own actions right here in what we perceive as a linear timeline. The thought experiments of time travel hold up a mirror to our own world, highlighting the interconnectedness of all things and the profound, often hidden, consequences of our choices. They teach us humility, reminding us that our perspective is always limited, and that even actions taken with the best intentions can have far-reaching and unforeseen effects. The ethical dimensions of temporal folding ultimately serve as a powerful metaphor for our own responsibility to the future, to history, and to each other in the present moment. They remind us that whether time is a line or a loop, the core challenges of morality, compassion, justice, and the wise use of power remain the central project of our humanity, demanding careful reflection at every turn. So where do we go from here? The journey to understand temporal loops is far from over. In many ways, it's just beginning, accelerating into a future powered by unprecedented technology and bold new theoretical frameworks. The next great leaps will likely come from a powerful synergy between massive observational projects and the mind-bending frontiers of theoretical physics. Gazing into the deep past, the James Webb Space Telescope acts as a cosmic time machine itself, peering back to the very first galaxies being born. But its incredible sensitivity isn't just about seeing farther. It's about seeing with greater clarity, hunting for subtle anomalies in the ancient light of the cosmic microwave background or the distribution of the earliest stars. These faint whispers from the dawn of time could hold the key, perhaps a strange statistical pattern, an unexpected polarization, or a temperature fluctuation that doesn't quite fit the standard model of a single, linear Big Bang. Such an anomaly could be the long-sought echo, the faint but definitive fingerprint of a pre-Big Bang universe, a cosmic cycle that came before our own, offering the first tangible evidence that our story is part of a much grander, repeating narrative. On the theoretical front, the quest for a complete theory of quantum gravity remains the holy grail. Current models like string theory and loop quantum gravity provide different mathematical languages to describe the universe at the smallest scales, where the fabric of spacetime itself is thought to be discrete or composed of vibrating strings. Both frameworks offer their own compelling visions of cyclical time. String theory, with its landscape of possible universes and its Ekpyrotic scenario of colliding brains, suggests cycles orchestrated in higher dimensions. Loop quantum cosmology, a derivative of loop quantum gravity, directly predicts a big bounce, with its equations naturally avoiding the singularity and replacing it with a quantum bridge from a previous contraction. The future of research lies in pushing these theories to make more precise, testable predictions. Can they forecast the specific spectrum of gravitational waves left over from a bounce? Can they detail exactly what the imprint of a previous cycle would look like on the CMB? The goal is to move these beautiful mathematical constructs out of the realm of pure theory and into the harsh light of empirical validation. Perhaps one of the most exciting new tools in this endeavor isn't a telescope at all, but a quantum computer. These machines, which harness the bizarre laws of quantum mechanics, are uniquely suited to simulating other quantum systems that are otherwise impossible to model. Researchers are already beginning to use them to simulate the conditions of the very early universe and to create tabletop models of wormholes. In the near future, we could see quantum computers used to run sophisticated simulations of closed timelike curves, testing how information behaves in a self-consistent loop, and probing the logical limits of causality without ever leaving the lab. They could help us understand the quantum behavior of spacetime itself near the Planck scale, potentially revealing how temporal order emerges from a more fundamental, timeless reality. This isn't about building a time machine in a box. It's about using quantum systems to act as analogies, allowing us to experiment with the rules of reality in a controlled, digital environment and gain insights that would take centuries to derive with pen and paper alone. The path forward is a collaborative marathon, not a solitary sprint, requiring astrophysicists, particle physicists, quantum information scientists, and cosmologists to combine their expertise. Each new gravitational wave detection by LIGO and future observatories adds another piece to the puzzle, constraining the possible ways the universe can behave. Each new result from particle colliders teaches us more about the fundamental forces that would govern a cosmic collapse and rebound. The future of this field is incredibly bright, defined not by a single eureka, a moment, but by a gradual convergence of evidence from multiple independent lines of inquiry. We are living in a golden age of cosmological discovery, where ideas once confined to philosophy and science, fiction are now being stress-tested with data and simulation. This relentless, multidisciplinary pursuit is a testament to humanity's insatiable curiosity, our deep-seated need to look into the abyss of time and not only ask how the universe works, but to genuinely understand our place within its possibly eternal, rhythmic dance. One of the most persistent and daunting myths about temporal loops is the belief that they inevitably lead to paradoxes, rendering the entire concept a logical impossibility. This idea has been popularized by countless stories where a time traveler accidentally prevents their own existence, creating a baffling causal contradiction that should unravel reality itself. However, this grim outlook is based on a fundamental misunderstanding of how physics might actually operate within a folded timeline. As we explored earlier with the Novikov self-consistency principle, the laws of physics appear to have a built-in mechanism for preventing such nonsense. The principle, derived from general relativity, asserts that any events within a closed timelike curve must be entirely self-consistent. This means that if time travel to the past is possible, your actions there were always a part of history. You couldn't kill your grandfather because in the consistent version of history you didn't. The universe would conspire through an infinite number of tiny probabilities: a slipped foot, a jammed gun, a sudden change of heart, to ensure that the timeline remains free of contradictions. Your journey to the past wouldn't change history, it would fulfill it. This transforms the narrative from one of chaotic paradox to one of elegant, predetermined stability, where loops are not glitches but lawful features of spacetime's geometry. Closely tied to this is the misconception that time travel would function like a cosmic undo button, granting a person unlimited power to alter events to their liking. This fantasy imagines a linear timeline that can be rewritten and edited at will. But that's not how most serious physical models work. In a universe where time can fold, the timeline isn't a document you can edit. It's a single, immutable sculpture. Your presence in the past was always there. Any attempt to make a significant change would simply fail, or worse, you might discover that your attempt to fix a problem was the very cause of it all along. This isn't a limitation. It's a fundamental property of a universe that operates on consistent, unbreakable physical laws. The potential for change isn't about altering a fixed past, but about fulfilling a role in a complex, interconnected whole. This doesn't strip time travel of its intrigue. It adds a layer of profound depth, where freedom and destiny are intertwined in a cosmic dance of cause and effect. Another widespread misunderstanding is the idea that a cyclical universe must be a stagnant one, where each cycle is an identical replay of the last, negating any sense of progress or evolution. This view paints a bleak picture of eternal recurrence as a pointless prison, where every joy and sorrow is destined to repeat infinitely without variation or meaning. However, this bleak outlook is based on a very narrow interpretation of cyclical models. Take the Big Bounce theory, for instance. While the universe might collapse and rebound, the conditions aren't necessarily perfectly reset each time. Quantum mechanics introduces fundamental randomness into the universe. This means that each cycle could have tiny, quantum-level variations in its initial conditions. These minuscule differences could ripple outward during the expansion phase, leading to a new universe that is similar to the last, but not identical. Over countless cycles, these variations could allow for genuine cosmic evolution, perhaps even producing universes with different physical constants or structures. In this model, the cycle isn't a perfect photocopy machine. It's more like a musician improvising on a theme, with each performance containing new nuances and variations. The cycles become a process of exploration, a way for the cosmos to explore all possible permutations of itself across eternity. This connects to a deeper philosophical error: the belief that predetermination within a loop negates free will and moral responsibility. If everything is going to repeat, the thinking goes, then nothing we do truly matters. This is a profound misreading of the situation. Your choices still matter immensely because they are an expression of who you are. In a self-consistent loop, your actions are not forced upon you by an external fate. They spring from your own character, your desires, and your reasoning. The fact that you make the same choice in every cycle doesn't make it less your choice. It means your character is consistent and authentic. Furthermore, in models with quantum variation, your choices in one cycle could potentially influence the quantum state of the subsequent universe, giving your actions a genuine impact on the future of cosmic evolution. This perspective doesn't diminish our agency. It magnifies it, framing our lives as integral threads in an infinite, ever-unfolding tapestry. Finally, it's crucial to distinguish the rigorous, math-based speculations of theoretical physics from the purely narrative devices of science fiction. While science fiction provides invaluable thought experiments and emotional frameworks for understanding these ideas, it often takes creative liberties to serve the story. A film might have a character dramatically altering the past to create a better future because it makes for a satisfying narrative arc, not because it's physically plausible. The real scientific pursuit is far more subtle and strange. It's about understanding the geometry of space-time, the constraints of quantum information theory, and the boundary conditions of the universe. By debunking these common myths, we clear away the sensationalism and get to the truly fascinating heart of the matter. A universe governed by elegant, consistent laws that might allow for structures as wondrous as temporal loops without breaking apart. This allows us to appreciate the real mystery and beauty of these theories, moving beyond the fear of paradox to a place of awe for a cosmos that could be so ingeniously and complexly structured. Have you ever walked into a room or started a conversation and been suddenly, inexplicably struck by the powerful feeling that you've lived this exact moment before? That eerie, fleeting sensation is déjà vu, a common human experience that has puzzled philosophers and scientists for centuries. While mainstream, neuroscience often attributes it to minor glitches in memory processing, a momentary misfire where the brain mistakenly labels a new experience as a familiar memory, this explanation can feel unsatisfying, failing to capture the profound and sometimes unsettling depth of the feeling. What if this common experience is something far more mysterious? What if, in those brief moments, we are catching a genuine glimpse through a fold in the fabric of time itself? This speculative but thrilling idea suggests that déjà vu might not be a brain error, but a brain glimpse, a fleeting crack in our linear perception through which echoes from another cycle of the universe or a neighboring timeline briefly leak into our consciousness. In a cosmos where time is not a straight line but a vast, looping tapestry, it's conceivable that our subjective experience of time could occasionally brush against these folds, allowing a faint whisper of a repeated event to break through, creating that uncanny feeling of having already been here, done this, exactly as it's happening now. This concept becomes even more compelling when we consider the peculiar nature of memory. Our memories aren't perfect recordings, they are reconstructions, stories we tell ourselves about the past. But what if some of those reconstructions are built from materials that don't entirely belong to our own personal timeline? In a cyclical universe model, where the same fundamental patterns of energy and information might replay across eons, it's not a huge leap to imagine that the specific configuration of neurons that fires to create a memory could be triggered not just by a current event, but by a resonant echo from a previous cosmic cycle. You wouldn't have a full, narrative memory of the past event because it didn't happen in your past. It happened in a universe that is, in a higher dimensional sense, parallel or prior to your own. The feeling is therefore vague, emotional, and devoid of detail, a haunting sense of familiarity without any source, precisely what people describe during a déjà vu episode. It's as if your consciousness is a radio, and for just a second, it picks up a faint transmission from a station broadcasting on a frequency from a different time. Now, let's turn to another enigmatic experience, synchronicity. This is the term coined by psychologist Carl Jung for those seemingly meaningful coincidences that defy pure chance. Like thinking of an old friend you haven't seen in years moments before they unexpectedly call you, or stumbling upon a book that contains the exact answer to a problem you've been struggling with. Jung believed these were not random accidents but manifestations of a causal connecting principle in the universe, which he called the collective unconscious. But what if the mechanism behind this, a causal connection, is, in fact, causal, just operating through a dimension we cannot perceive? If time is folded, then events that appear separate and unconnected in a linear timeline could actually be intimately linked through a higher dimensional shortcut. A thought in your mind today and a phone call from a friend tomorrow might not be two independent points on a line. They could be 2 points that are touching each other through a fold in the time dimension, creating a loop of cause and effect that appears instantaneous and magical from our limited perspective. Imagine spacetime as a vast, crumpled piece of paper. Two points that are far apart on the flat surface can be brought into direct contact by a fold. In a universe with temporal folds, your intense thought about your friend could be the effect of their future decision to call you, with the influence traveling back along a fold in time to inspire the thought that seems to precognitively predict the call. This wouldn't be prophecy, it would be physics. The call causes the thought just as much as the thought anticipates the call, in a self-consistent loop that our linear brains are forced to experience as two separate, mysteriously connected events. These synchronicities, then, might be the places where the hidden architecture of a folded reality briefly becomes visible, like the stitching showing on the seam of a garment. They are moments where the universe's underlying connectedness, its intricate and looping geometry, pokes through the veil of our everyday linear perception. Of course, it is crucial to emphasize that these ideas are, for now, highly speculative thought experiments rather than established science. There is no direct empirical evidence that déjà vu is anything other than a neurological phenomenon, and synchronicities can often be explained by the law of large numbers given enough people and enough moments. Incredibly unlikely coincidences are statistically inevitable. However, the power of these theories is not in their immediate provability, but in their incredible ability to bridge the gap between the deeply personal, subjective mysteries of human consciousness and the grand, impersonal theories of cosmic physics. They take experiences that feel profoundly meaningful to us as individuals and offer a potential framework that connects them to the fundamental nature of reality itself. This transforms the cosmos from a cold, mechanical void into a place that is potentially resonant with meaning and connection, where our inner lives and the outer universe might be woven together by the same temporal threads. It invites us to consider that the strange flickers in our perception are not just glitches, but might be tiny windows into a much larger, more mysterious, and more wondrous reality than we ever imagined. But if the universe truly does cycle through endless iterations of birth and death, a profound and haunting question emerges. Are we, as conscious beings, merely along for the ride, or could consciousness itself be the entire point of the cosmic process? This idea ventures beyond the cold mechanics of physics and into the realm of philosophy and metaphysics, suggesting that mind and cosmos are not separate, but are deeply entwined partners in a grand, evolving dance across the folds of time. Some interpretations of quantum mechanics, most famously the Copenhagen interpretation, place the act of observation at the very heart of reality. In this view, a quantum particle exists in a fuzzy cloud of probabilities, a superposition until it is observed or measured, at which point it collapses into a definite state. This has led some physicists and philosophers to propose that consciousness itself is not a passive byproduct of the brain, but an active participant in shaping reality. If this is true, then the way we perceive and interact with the world could fundamentally influence how time itself unfolds around us. Our observation might not just be recording events. It could be solidifying one possible timeline out of many, effectively choosing the path of actuality from a sea of potentiality. In a universe with temporal loops, this role becomes even more dramatic. A conscious observer traveling a closed time-like curve wouldn't just be a tourist in the past. Their very act of observation could be the stabilizing force that ensures the loop remains consistent and paradox-free, their mind acting as the needle that stitches the timeline together into a coherent, self-consistent whole. This perspective radically transforms our place in the cosmos. We are no longer insignificant specks in a vast, impersonal machine. Instead, we become integral components of the universe's functioning, our awareness acting as a kind of cosmic glue that holds reality together, especially in its most bizarre and folded regions. This idea finds a powerful echo in the Anthropic principle, which we discussed earlier, but pushes it even further. It's not just that the universe's laws are fine-tuned for life. It's that the universe might be fine-tuned for consciousness itself. Each cycle of a big bounce or each new bubble in an eternally inflating multiverse could be an experiment in complexity, with each iteration providing a new opportunity for awareness to emerge in richer and more profound forms. In this breathtaking vision, mind and cosmos co-evolve. The universe provides the physical stage with its laws and constants, and consciousness emerges to observe it, and in doing so, completes it. Then, in the next cycle, the universe might be reborn with slightly different parameters, perhaps ones that allow for an even more expansive or unified form of awareness to blossom. The cycles of time become a learning process, a way for the cosmos to explore not only different physical forms but different states of being and knowing. This bridges the gap between hard science and spiritual intuition in a truly fascinating way. For millennia, Eastern philosophies have taught that consciousness is fundamental, the primary ground of all being, and that the physical world is a manifestation of it. The Hindu concept of Brahman or the Buddhist idea of the ground of awareness point to a universal consciousness that underlies and permeates all of reality. The theories of cyclical time we've explored provide a potential scientific metaphor for this ancient wisdom. The endless cycles of creation and destruction, the kalpas and yugas, are not just physical processes but spiritual ones, an eternal rhythm through which consciousness experiences and knows itself in an infinite variety of ways. You are not a separate self looking out at a foreign universe. You are the universe itself, temporarily localized into a particular point of view, experiencing its own grandeur and mystery from the inside. Each life, in each cycle, is a unique perspective that the cosmos uses to understand itself more deeply. The temporal folds are then not just wrinkles in spacetime, they are the folds in a vast, cosmic mind, allowing different moments of experience to touch and inform one another. This challenges us to fundamentally rethink our relationship with existence. It invites us to see ourselves not as passive victims of fate in a predetermined loop, but as active, purposeful participants in a cosmic story of awakening. Your choices, your struggles, and your growth are not meaningless echoes in a void. They are contributions to a vast, collective journey of consciousness through time. Whether this journey spans a single lifetime or an infinite number of cycles, the ethical imperative remains the same: to expand awareness, to cultivate wisdom and compassion, and to align ourselves with the evolutionary current that moves toward greater light and understanding. This view infuses the potentially cold concept of cyclical time with profound meaning and responsibility. It suggests that the ultimate purpose of the cosmos's great loops and resets might be the gradual, patient cultivation of a universal consciousness, a state where the universe becomes fully aware of itself, not in fragments, but as a whole, integrated and enlightened being. And in that possibility, we find a hope as vast as the cosmos itself, that every end is truly a new beginning, and that each of us, in our own small way, is helping to write the next chapter in that eternal story. We have journeyed together through the captivating landscape of temporal loops and cosmic cycles, from the ancient intuition of eternal return to the cutting-edge mathematics of closed time-like curves. We've seen how time might not be a river flowing in one direction, but a Möbius strip, a spiral, or a vast, static block where every moment exists simultaneously. These are not just abstract ideas for physicists to ponder. They are profound invitations for all of us to reconsider our most basic assumptions about reality, about fate, and about our own place in this breathtaking cosmos. Whether the universe breathes in a grand big bounce, collides with a parallel brain in a higher dimension, or simply allows for tiny time crystals to tick in a lab, the overarching theme is one of magnificent repetition, a suggestion that existence is far richer, stranger, and more interconnected than our linear daily lives would ever suggest. This journey challenges us to find a new kind of humility and a new kind of wonder. It asks us to hold two seemingly contradictory ideas in our minds at once: the powerful, visceral reality of our lived experience, where time flows, choices matter, and the future feels open, and the staggering possibility that from a cosmic perspective, all of this may be part of a single, eternal, and unchanging whole. This isn't a call to despair or nihilism, but quite the opposite. It is an invitation to see our lives as integral threads in an impossibly vast tapestry. If our actions are part of a cycle, they are not diminished, they are echoed. If our consciousness is a way for the universe to know itself, then our curiosity and our search for meaning are not trivial. They are the cosmos awakening to its own mystery through us. So what do we do with this knowledge? We let it expand us. We let it fuel our sense of awe every time we look up at the night sky. We let it deepen our compassion, understanding that everyone we meet is on their own incredible journey through the same mysterious folds of time. And most importantly, we keep asking questions. The greatest achievement of science is not providing final answers, but forever refining the questions we ask. Each theory we explore, from the Ekpyrotic model to the holographic principle, is not a destination but a stepping stone, a brighter lamp helping us see just a little further into the darkness. The universe's secrets are endless, and the conversation about its nature is the most exciting story ever told. Your curiosity is the most important part of that story. So let's keep wondering together. Share which theory resonated most with you in the comments below. Was it the quantum timelessness, the ethical weight of the eternal return, or the sheer grandeur of the Big Bounce? Let's keep this discussion going. If you enjoyed this deep dive into the folds of time, please subscribe and hit the bell so you don't miss our next journey into the mysteries of space and reality. Thank you for watching, and never stop questioning.